Verma has guided more than 15 PhD candidates in the experimental and DFT-based theoretical studies on electrochemical and optoelectronic materials. He has various international collaborations and organized many international national conferences, workshops, and continuously giving training on of DFT-based tools to national, international faculties and scholars. Recently, his two courses of DFT and molecular modeling using Siesta tool under the scheme of skill development and informal education of Swami Vivekanand Technical University is running successfully, in which more than 200 participants have been trained, out of which 20% participants were out of India. He has also delivered more than 40 invited talks in various national, international conferences and workshops. He is an active life member of several professional bodies like National Society of Solid State Ionic, Material Research Society of India, the Society for Advancement of Electrochemical Science and Technology, Karaikudi, etc. And is passionate about contributing to scientific development through his research activities. Now, I'll hand over this session to Dr. Mohanlal Verma, sir.
Thank you, Dr. Gaurav. My voice is okay?
Yes, sir.
It's okay?
Yes, sir. Yes.
Okay, so should I start now?
Yes, sir. Dear participants, sir, 1 minute. Dear participants, please be muted. If you have any concern, any question, we'll discuss later. At the end of the lecture, we can discuss. Kindly cooperate.
Okay, so thank you, Dr. Gaurav and his team for this invitation, and I'm very happy to be the part of this international FDP that hands-on sessions related to System 1, and this is one small talk on DFT implemented in System, and definitely we are concerned with that nanometer material research. So first of all, I would like to thank my guide, Dr. Professor Rakesh Chandra sir, and especially that Dr. Ravi Pandit sir, and, because of his pioneer work in India, and also we have started this type of workshop with the guide of and the blessing of Professor Ravi Pandit. And this is our 10th workshop or FDP program concerned with this system and related tools. And my friend Roderick also, because he motivated me to do some valuable work on this system. And my research team, so that Dr. B.K. Shorov, and these are I actually concerned with related to that all three components of that material research, that is mathematical modeling, experimental, as well as DFT. So these are my students, and Dr. B.K. Shorov is my first student, and now he's the sixth expert in this team. And these are my DFT team, and people are doing wonderful work on different materials, different projects. And this is the location of my institution, the Sri Sankaracharya Technical Campus. This is situated in Bhilai, Chhattisgarh, full of green trees and a very peaceful region. And I always welcome people to visit Bhilai and my institution. That also with the collaboration in this sister team. And this is my lab, the glimpse of my lab. And the first picture, this is the picture of my first workshop, that is actually the benchmark at 2030, and this was the time that is was started at 21st June. So we are in the same era, but that is 2013. And Dr. Rodrigo is with us, and now we are running the 10th one. Two next workshop is will be scheduled. The first one is in October in 23rd Shankar, and probably in February in IUC Delhi also. So this is really a good work in collaboration with different experts all over India and out of India also. This is headed by Sir Professor Ravi Pandey sir, and this is actually the work. First thing, the introduction of that this international FTP. Always it is done by Professor Ravi Pandey sir, but because of that time gap as well as the time zone, he is going to deliver his talk in today evening 6 p.m. I am doing on behalf of him, his blessing. We are to hear. This is that schedule and some topics I mentioned here, and the talk will be, so this is scheduled two part. The talk will be 40 to 45 minutes, and after that there will be 10 minutes break, and then we will start that hands-on session. And our work, this this is focused on hands-on session, and definitely I promise that you will enjoy that hands-on session. But for that you have to just cooperate with us and try to do whatever that this instructor or the experts of hands-on session will teach you. So that different experts are with me. So that the hands-on session will be for 90 minutes and 20 minutes that discussion per day. So they will enjoy definitely. And this is the team, and which is published in the brochure. So let's begin the talk. I will not take much time, and please mute your mic. Request, please. Okay.
Raju sir, please, Raju Viramala sir, please mute yourself. The session is already started. If any query, anything is there, please ask in the last. And if you are chatting with someone,
Hello.
before that, you please mute it. It's a session, no, that we
Yes, sir.
have given time to
Sure.
each and every speaker. So please maintain that dignity, that discipline. Thank you. Please do that.
Okay, so let's begin with this, and we are familiar with the terms that nanomaterials, nanotechnology. These are nowadays people are using who are directly and indirectly engaged with material research. So definitely, it is defined with the material, which size is in the range of that 100 1 to 100 nanometers, and at this scale we know that the quantum effects dominate and creating opportunities for materials with the revolutionary properties, and this is that some diagrams related to that carbon based nanomaterials, and the significance of these nanomaterials. We better know that these materials form the foundation of emerging technologies in electronics, medicine, energy storage devices, and environmental remediation. And this unique behavior enable innovations impossible with conventional material. And main example is that is the graphene and graphene based materials. Also, we have that graphene structured material similar to that graphene, and that quantum dots and having that tunable optical properties, carbon nanotubes, and so on. So this is now a very rich field of research, and so many papers are being published annually on this material. And then the second term we will deal with, that is the fundamental of density functional theory. And I'm just giving some glimpse here because the detail of this detail of its fundamental of density functional theory that will be deal with Professor Ashok Kumar from Central University Punjab. So that this DFT, this represent a revolutionary quantum mechanical modeling method used in investigate, especially that electronic structure of many body system. And rather than working with complex many electron wave function, so when we think about that quantum physics where we are using that Schrodinger equation, and there we have the concept of the wave function and the solution of that Schrodinger equation by using many electron system or many body system, it's very complicated. Then the thing it is this many electron system, it is converted with a single electron system, that is related to charge density, then this DFT comes. So rather than working with complex many electron system, DFT uses electron density in its fundamental variables. And this is dramatically simplifying this quantum mechanical calculation required for material simulation. So this will be detailed by Toshio, and there we will have some practical implementation of this in some computational code, and we will discuss about that Kohn-Sum equation, and that has a Hohenberg theorem in detail. So this is actually the theoretical foundation in stabilizing this electron density as a key variable. And this Kohn-Sum equation is converting many body problems to a single electron equation. Now the question is DFT, why it matters for nanomaterials. So definitely this is very useful for the property prediction. So DFT accurately predicts electronic structure, magnetic, and properties of nanomaterial before synthesis, saving valuable research time and resources. So in general, I am also concerned with that experimental research one. So I know that for that experimental, it's really costly, and several times we just use try and error based experiment, so that actually um, we are just wasting our valuable time as well as the cost of that equipment. So before designing any particular device, we should a particular device or particular material, we should go through this DFT based study, and this actually predict properties which is useful for the fabrication of any device. And another one is that is atomistic insight. So this provides atomic level understanding of material behavior, and this is impossible to obtain through experimental techniques alone. So in the FT, we are thinking about the properties of that material up to the level of electrons. And then this rational design. So this enables computational screening of thousands of potential material, accelerating the discovery of nanomaterials with targeted properties of specific applications. Now this next term, why this system? Because these are that terms we are using in this FGP, that density function theory, and this is system. So this is the next term I would like to introduce here. So what is system? So this is actually the Spanish initiative for electronic structure, electronic simulation with thousands of atoms, and definitely it is Spanish based too, and which has a capability to simulate large atomic system efficiently, making it ideal for complex material structure. And one good thing that is this is one open source DFT program. So in my lab, I use all the tools and the utilities which is free of cost. So this is also the open source course. So this open source density functional theory implemented in Sista has forced a collaborative global community of developers and users continuously improving its capability. And it has now 25 plus years of development. So the first Sista is first released in 1996, and it evolved into the sophisticated simulation tools widely adopted across academic and industries. Now the historical development. So in early in the 90s, so this conceptual development begins in this university under the leadership of Emiliano Artecho or Pablo Ordezon, and this is the first one. And then after 6 years, the first published release of system code is introduced with this linear scaling approach to DFT calculation. So what is that linear scale approach? That will be detailed by Dr. Ashok. And, this in 2000, this rapid adoption by the scientific community with significant features expansion, and now it presents over 7,000 academic citations and stabilizing SIST as a cornerstone in computational material science. Now, comparable with other DFT code, there are so many DFT codes people are using, and some main codes that we generally heard about this SISTA, WASP, quantum expression, administrative, Gaussian, and so many things. So let's compare this tool with others also. So that SISTA is the strength is it's a memory efficient, fast for a large system, and this use linear scaling. And the WASP, this is high accuracy with these extensive functionals. Quantum expression, this is a plane wave based accuracy, and many post processing tools are there. Happening is extend for response properties. And the limitations of SISTA is it has a limited exchange correlation function, and the WASP is it's a costly license. This is not open source, and high memory demand is by this course. And also this quantum espresso is computationally intensive for the large system, and even it is a steep learning curves, and based use cases, that is you can use this system for nanomaterials, some biological systems, surfaces, and WASP you can use this for metal, complex oxide, detailed electronic structure, and quantum espresso that periodic system, phonon spectroscopy. All these tools, other tools are also good for that periodic systems, and this and even it is good for this vibrational properties and dielectric response. So this systems competitive advantages lies in the ability to handles large-scale system efficiently, making its preferred choice for the nanomaterials and biological simulation. And while other codes may offer high accuracy with certain properties, and the SIST actually balance the accuracy and performance, it often unmatched for the complex materials. So for the complex material and the heavy materials, one should use this system. And for that, the small materials, WASP is good, but it is not freely available. So that Sista's modular architecture. So this actually use this real space grid. So we use this real space and approach for representing electron density and potential, optimizing calculation for complex geometrical typically in nanomaterials. And it uses numerical atomic orbitals. So this numerical atomic orbitals is a basis set. So all these terms we will discuss later during hands-on session. Also, we will discuss what is that basis set and what is the meaning of these numerical atomic orbitals and what is that real space group. So time to time you will understand. So these are the terminology used in that DFT or system-based systems. And this parallelization, so advanced parallelization computing capability allows system. Parallelization means we have numbers of processors available in our desktop and laptop. So we can use all the processors at a time. That is known as parallelization. So this system is good for this advanced parallelization capability. And that's suitability for nanomaterials. So the system's unique implementation make it particularly well suitable for nanomaterial research, and it's a really computationally efficient for to handle that 5,000 plus atoms using moderate computing resources, and it's flexible for all dimension. We can work with zero dimension, one dimensional, two dimensional, definitely that three dimensional bulk system also. And but before that, we can validate its accuracy. So extensive benchmarks against experimental data and high level calculation we can do. So its ability to balance computational efficiency with accuracy allows researchers to study complex nanometry that would be prohibited expensive to simulate using other implementation. So this is good tool to study that nanomaterials in almost all dimensions. So that core DFT implementation in the system. So these are the terms we use in a DFT, that the exchange correlation function, that is LDA, and that second exchange correlation function, that is ZZA. So this in LDA, this assumes electron density varies slowly. So it's almost constant, and it's throughout that system, and this is computationally efficient. And in the gradient, generalized gradient approximation, the gradient of this charge density distribution is there, and this is better for molecular system. And by default, in general, we use the GGA because in many properties GGA is working good. And this spin check polarized calculation, so this enable in system. So for the study of that spintronic or magnetic properties of that materials or magnetic nanoparticle, we can use this. And this implementation efficiency is also there in core part of this system. So it optimized algorithm for solving Poisson equation. This is one equation in place of that
Okay, then already last movie for the employee. Okay.
So in the system, we have this exchange correlation support, LDA, GTA, and for that interaction of one molecule with that surface, that is the terms related to van der Waals type interaction. So we can use this one functional, and there are so many other custom functions out there. So these are some functional exchange.
నాకు క్లియర్గా ఎంఈసి ఎంఈసి
Understood that our price is just currently following it more than every
నెక్స్ట్ సోడియం నైట్రేట్ ఇక్కడ కూడా క్రోమో ఐసోలేషన్ చేస్తుంది ఎంత వస్తుంది
Is there any question?
70%.
Dr. Gaurav, so many disturbances are there. So in sister tool, we use that the pseudo potential. This pseudo potential is actually we use that non-conserving pseudo potential. So what is actually that pseudo potential means? So generally in uh, calculation of that method, we have two methods. One is all electron method, where in spite of that nucleus, we have different electrons here. And if we solve this, that the Schrodinger equation or Bohr's equation for all these electrons, so this will be very complicated. So in spite of that, we think about this valence electron. Only this is valence electron, and the effect of this nucleus and other core electrons on this valence electron, and this accumulative, this is named as that pseudo potential. So we will use these terms further. So just generally that sister uses pseudo potential, and this is pseudo potential based utility, where we have the valence electron and the effect of that core electron and nucleus on that valence electron. So accumulative terms is a pseudo potential. So this sister implies TM pseudo potential that accurately reproduce all electron results while significantly reduce computational cost. So the developers actually working to control that computational cost. So for that big system, that's why this is used in system. And that relativistic option is also there for the in the pseudo potential. So what this relativistic option, so that scalar relativistic and non-relativistic pseudo potential are there. And some we have generation tools of this pseudo potential, so we can use atom. This is one program. By using this, we can generate that pseudo potential. And also we have some good pseudo potential libraries available in internet. So either we can download that pseudo potential from those libraries, or we can generate that pseudo potential. And generally, it's that sister team recommended that one should generate that pseudo potential of any specific system. So this is actually the heart of that elements, and that's the sister program we use. One more thing, that is the basis sets and the real space grid. So these are the terms. So generally that system uses this numerical atomic orbital basis set, and these basis sets are classified as a single zeta, double zeta, triple zeta, and that with polarization also, that we have single zeta polarization, double zeta polarization, and also that triple zeta polarization we can use. So there's the real space grid, means we can use that XYZ axis where that real space, and we can use as a grading of that. So this actually control that the efficiency and also that efficiency and the computational accuracy. So now the system workflow. So generally we know that the computer is a dumb box. We have to keep each and every information to that system. So we start with that input file preparation. So we give this is the screenshot of that one of that input file. So in hands-on session we will develop this type of input file and how to generate this input file we will discuss. And in the input preparation, generally we define that atomic geometry and species. So this is that atomic geometry in terms of that coordinates and these lattice vectors and lattice parameters. And also that we said that is been sorry, that basis sets and superpotential we will make. And that here this gallium oxide, so we think about the calcium oxide. And then self consistence field cycles we will involve this. And then the post processing utility we will use. So similar to that experimental method, in experimental method we design material, then we process it, and after processing that we have this final output. So and in that final output we characterize that, we study different properties, and then we develop any particular device or use that material in particular device. Similarly here also we design that structure, we prepare that input file, and then we optimize that system. And after studying its various properties, we get some characteristic of that material, and after that we find that this material is applicable for any specific device or not. So that this the first term, that is the geometry optimization structure prediction. This is a very crucial important part, and part of this system based study. So we start with that initial structure. So either we design this structure by using any tool. So we have different pre-processing tools, or we can also take that initial structure from internet or some experimental data we can get as an initial one, and then during this optimization we calculate its force and also that energy terms. Optimization means we have to modify that structure for the lowest minimum potential energy, and that energy minimization is there, and then structure is completely relaxed before calculating its various property. So we will adopt this various method of optimization, and will deal in hands-on session how to optimize that material, how to design that material. So every part will be covered in hands-on session. So that's this types and skills. So definitely we can do with, as I mentioned, that this system is capable with all types of materials. So that zero dimensional materials, so this quantum dots, nanoclusters, or fluorines, this can be modeled with the system, and revealing this quantum confinement effect with its unique properties. And these one dimensional materials are carbon nanotubes, some semiconductor nanowires, some molecular chains, and this can be efficiently simulated, capturing their distinctive transport and mechanical characteristics. And in the two-dimensional material, we can use that graphene or graphene structured material, some transition metals, dichalconides, and other two-dimensional materials. So this can be extensively studied, predicting their electronic, optical, and thermal properties. And this system can handle system with thousands of atoms, enabling a realistic simulation of complex nanomaterials. And then some properties. Generally, we use this system to calculate the fundamental. Apart from that, it's a structural properties most important. So after optimization, we study its a structural property, and after then we start that electronic structure calculation. So we just study its a band structure. Definitely, we know that all the optoelectronic devices, it is discussed with that it's a band plot. So we can have its a band plot by using this system tool, and this density of states. So this is also shows that the band gap and conduction band, valence band, and other things. So all these things we will discuss, and then this charge density visualization. So since all the properties we know, it is the function of the distribution of electrons or distribution of charge. So the charge distribution, this can be a charge density can be visualized by using different post processing activities. So in electronic structure, we will deal with band structure, then density of states, and projected density of state also. So this projected density of state study, that is known as PDAS. And here we will observe the contribution of different orbitals in density of states or in conduction band and valence band. So we will study this band analysis on our computer screen using. Also, this is good for that defects and doping in material. So one good thing with this safety is we can manipulate uh, that structure of any materials as per our choice, as per our expectation. So we can just dope some foreign elements, foreign atom. We can pull out some atoms to create defects, and we can change its shape and size. So everything is there. So defects and impurity, these are actually playing a key role, especially in the optical properties of material, magnetic properties of material. So we can use this tool to study all this one. And this system enables a precise calculation of defects formation energy also. And especially that the
Crossing
semiconductor
మీద
can, can determine how dopants alter electronic structure, chemical structure.
దాని ముందు క్రాసింగ్ చేయడానికి హ్యాండ్ అయిపోతాయి.
But to create a doping, one thing that is important, that is we need that large supercell. Uh, this is typically required for the study of defects. And also we can use this system for the treatment of surface and interfaces. And for example, we have that battery system, and in battery system we have electrolytes and connected with are sandwiched between two electrodes. So there will be the interface between that electrodes and electrolyte. So that interface can be studied by using this tool, and for that we can create that vacuum layers, and we can specify different layers also. So researchers can investigate surface reconstruction, absorption phenomena, and interfacial property for vital catalyst sensing and electronic application of nanomaterials. So generally, that chemistry people uses the surface properties of that material, and the catalysts are there. So this is a very good tool for study all these things. The transport and optical properties, this is also very good. So we have this for different optoelectronic devices. We generally have this current voltage characteristics. So by using this transport properties analysis with this transistor, this is one inbuilt tool with transistor. We can have this current voltage characteristic, transpose spectra, quantum interference effect, and the thermoelectric properties. And nowadays, what term is that quantum transport? This term is used, so we can study quantum transport by using this. An optical property, definitely that dielectric function, optical absorption, refractive index, extinction coefficient, and that excitance effect. So all these we can study. But if anyone wants to that study that luminescence type property, so this is not the ground state property. For that we use time dependent density function theory. And then these are some advanced capability, transport and magnetism. And for that, some terms we use is spin orbit coupling, non-linear speed. These are some terms used in transport, non-equilibrium green function. So these are the terms we use in the study of these transport properties and magnetism. So time to time we will learn about them, because we have 2 weeks to understand all these things. So I'm just giving here the claims are some using some terms, and we will detail later. So molecular dynamic simulation, also we can perform this molecular dynamic simulation by using this. So this molecular dynamic simulation is generally divided into classical molecular dynamic simulation, and the quantum one. And by using this sister tool, we use that quantum, which is actually named as AIMDS, AB initio molecular dynamic simulation in sister. This combines actually the quantum mechanical accuracy with the classical trajectory simulation, allowing the researcher to investigate dynamic process like diffusion, phase transition, reaction mechanism. So if anyone want to study that electrolytic properties in the cell, batteries, supercapacitor, then we can calculate the diffusion coefficient. And phase transition means the effect of temperature, pressure on the system, and that reaction mechanism. So for that we can use this molecular dynamic simulation, and definitely we use this every initial molecular dynamic simulation. So one of my courses written on this special topic. And unlike classical force field, this AIMD captures bond breaking information accuracy, and typically SISTA AIMD simulation span picoseconds to nanoseconds, providing valuable insight into thermal stability, kinetic pathway, and temperature dependent properties of material from the first principle, starting from zero. So we can have this force calculation, so quantum mechanical force from electronic structure, and this integration of Newton's equation of motion, and this trajectory analysis regarding position and velocity over time, and the property excitation is the fourth step of this molecular dynamics approach, is the calculating time dependent observation. So this is really very powerful utility, powerful tool available with the system. Catalytic and surface chemistry, yes, that's the mechanistic insights we can deal with that. So sister simulations reveals the step-by-step pathway for uh, carbon dioxide activation on copper zinc oxide interfaces, identify key intermediate with transition state. Energy barriers, one can calculate the precise activation energy by each elementary steps in reaction. Surface modification, this can be performed by using this particular utility. So this collaborative study between computational and experimental group demonstrated SIST is a powerful tool in the rational catalytic and design. And people starting from the starting, people are working with that DFT with the graphene structure material. So this is that case study of graphene. So here this 1.42 angstrom bond length, it is observed by using this DFT, and this is only 1% deviated from its experimental value. And this is single plane of that carbon, and this optimized structure serves the foundation of subsequent property calculation. that electronic structure, Dirac cone type of property, it is observed in graphene. So it is experimentally as well as theoretically, DFT based theoretically, it is observed that, and it's a really good one. And now it is advanced in form of that graphene structured materials like zinc oxide and the silicon, zircon, like that. And the SISTA effectively models various defects in graphene, including vacancies, stonewall defects, and other things. Nanowires and nanotube simulation. So we can design that silicon nanowire, carbon nanotube, and we can use that strain engineering. Means we can apply strain on that material, and we can change its property, specifically that its electronic property, that band gap modulation. This is known as band gap engineering. So that's a really wonderful study on that, especially that nanotube or the chain of that material using DFT implemented in system. So high throughput in automation. So the integration of system with the modern computational frameworks like Python. So nowadays people are running behind this Python and Python based tool. So System is also interfaced with AAC, atomic simulation environment. This one AAC, and this and also that IDA. These are some terms computer people are using. So AAC is a really good interface, and where this we can automate all the workflow with dealing workflow with that system, and we can manage this data by using this IDA. And these tools enable researchers to automate complex workflows from initial structure generation. So, from the basic learning of this system, if you move to this AC based tools or this IDA, then this really that will be very impactful research on the material. Recent development. So recently, that hybrid functional implementation are being made, and this system is optimized for to use that enhanced HPC skill. So that is HPC scaling, another thing that will be discussed by Mr. Abhishek from that IOC Delhi. So that how one can use this HPC for sister related tools, and that for the recent development that European Max collaboration are doing good. And nowadays people are using this machine learning integration with system. So one of the talk in this FGP. This is on machine learning, and definitely professor from Malaysia. He will deal with this machine learning with this ability. Limitations. So that one limitation always experimental just says that this LD and GGA, these are the functional DFT standard DFT functional, and we are using. And actually, this underestimates the band gap or band gap in the 30 to 50%. And this is not only the problem with this system, but all the tools is concerned with the DFT. They have this limitation, and you can overcome this limitation by using some that GGA plus U Humbert correction or that hybrid function. And that the second one is that excited state limitation. So this is the ground state property. So for luminescence type property, if you want to study, then we have to move beyond that this DFT to that time dependent DFT or that GW type utility we have to use. And that computational scale. So that scaling, the efficiency is up to 10,000 atoms. If you
కానీ
have more
ఎంత
than
తేడా
10,000
ఉన్నదేనో అసలు
then
మన
this will create issue. So that more memory is required when we move from the more than 10,000 items. Conclusion and future prospects. So this is that this actually accelerating that material discovery, and the DAXA scale computing there, AI integration is with the system. So this is community driven innovation. So you can work on this, and if you have some issue, then you can take the help of the community. So we look to the future system is positioned to remain in the forefront of the computational material science, bringing the gap between quantum mechanics and real world application. And the combination of algorithm innovation, hardware advances, and interdisciplinary collaborations promises to unlock new frontiers in the material discovery. So this is a really good tool, and me with my team using efficiently this one. And just so in my team, we are using this utility. I think this is right. Anyway, so thank you all, and it's already 11. Just the rest of the part I will continue during my hands-on session. Uh, so thank you, and it's 11 o'clock already, so we should move to that 5 or 10 minutes break, and then we will start that hands-on session. Some here at my YouTube. Thank you.
Thank you, sir, for your wonderful lecture on how to use Siesta for DFT and other computational calculations. So now participants, they can ask their questions. Pooja Srivastav, you can ask your question.
Uh, Hello. Good morning, sir. So thank you for your very good lecture. Sir, I have one doubt. Actually, I have used WASP and Quantum Espresso till now. So, and you were telling us that, I mean, Siesta can deal many atoms compared to WASP or Quantum Espresso
Yeah,
in
hello.
yeah, sir. So, what are the things which are compromised here in the case of Siesta, which are not compromised in the case of WASP and Quantum Espresso?
So
So, this is my
generally,
first question. And second question, you were telling us that, I mean, 0D materials can also be treated well
yes,
in Siesta, but
yeah.
mostly I have had heard that, I mean, like in chemistry, they use Gaussian, especially
Mm.
for the molecules. So molecules are also 0D materials, so that
Yes, yes,
also
yes.
can be treated using under periodic
System.
boundary condition, using WASP or Siesta or Quantum Espresso.
No,
So
that zero-dimensional material that good in Gaussian also, and for that isolated system, Sista is good, and Sista is computationally effective. Means by using your simple laptop or desktop, you can run Sista. And this that quantum expresso and WASP, but this actually take that computer that is computationally expensive. For a small system, you can use WASP. That can a small time, but if you have that large system, about 100 atoms or more than 100 atoms, or the polymeric materials with more than 100 atoms, then one should use this system. Okay, so this is good.
yeah, yeah. So is there any compromise with in which Siesta does to treat bigger systems?
No. It's a good. I have tested it. It's a good enough. Not compromised. Even that accuracy is better. Even time to time, that accuracy is increasing. Yes, the version is increasing. Now we are using a system 5.4.0, and it's really accurate enough. And one good thing, this is open source because the people, the WASP is actually commercially available. It's a good tool. People are using because it's user friendly, and uh, one can use that easily. But it is really commercial one. This is open system, so and easy to learn
And
also. Yeah.
what about the Gaussian comparison
Gaussian
between
is
Gaussian and Siesta?
Gaussian is good. Gaussian is good for the solution. I mean, this is not very good for solid materials, periodic materials. If you are using that chemistry, more chemistry you are using, then you can go through that Gaussian. Gaussian is also good. But for the chemistry people working on that solution and like that, this type of volatile systems are there. So this is good.
Thank you, sir. Thank you.
Any other question? Participants, any other question? No questions?
Yeah, I'm available next 15 days. So during that hands-on session, we can discuss everything. Okay.
Okay, sir. We'll break for 10 minutes, then we'll come back with the hands-on training.